So thanks for the introduction and organizations. I am very happy to give a short talk for one of my favorite results recently. And this paper is just uploaded to arXiv, I think less than 1 week ago. And this is John work with Lipschitz. Okay, so let me give you a first glimpse of what we have done. So we start with a Lipschitz domain. We usually think about this as a bounded Lipschitz domain. And then if we consider so-called the Rychkov extension operators on that, and we studied two aspects to these operators. The first one is that we are able to find certain kind of operator E alpha beta that has similar extension to E, such that if you have a derivative outside, then we can sort of move this derivative inside, and then we have this kind of commuting properties. And the second one is that if we think about extended functions outside the domain, and then this, no matter how rough this function we started with, the extended function will always be smooth. And then we deduce certain kinds of quantitative smoothing estimate. So we sort of want to talk about the blow up of the gradients up to the boundary. So in the talk, I will keep using this notations, the S prime omega, to be the restrictions of the Campbell distribution on the domain. So it's a subset of a distribution space. Yeah, and then there are a couple questions I need to answer. So yeah, what is the Rychkov extension operator? And then we talk about the expressions of this E alpha beta. So what is the expressions of this E? And then finally, I think I will spend maybe 1 or 2 minutes to talk about those characterizations. What kind of quantitative estimate do we have for the space? Yeah, so let me just mention a little bit about what's the extension operator. So if we have a subset omega, and if we have a function f defines an omega, then an extension of this f is a kind of function f tilde defined on the whole space, such that if we restrict the f back to the domain, it will equal to f. And then extension operator is a map that maps the certain kind of f to certain kind of f tilde. So in our cases, we only care about linear extensions. So we don't need to limit our focus on just the extension of functions. We can talk about extension of distributions as well. So in that cases, the extension operator can be defined as left inverse to the natural restriction map. So the extension problem asks, so can we find some kind of extension operator which is bounded in certain given kind of function classes X? So this function classes X, you can take wherever you like. You can think about it maybe classical CK space, maybe Sobolev space. And then in our cases, we mostly will focus on the best of space, BPQS space, and the triple resolving space, FPQS space. So maybe let me start with several examples of extensions. So we can talk about the most trivial and dumb extensions, which is setting the extended function to be identical to 0 outside the domain. And certainly this kind of E0, it's bounded in LP, but certainly does not preserve any continuity. So you can see that if you have a continuous function and you just try to extend it, very likely you will have discontinuity at the boundary. This is not a good space to talk about. So this is not a good extension operator that we are going to talk about. And a better one is mostly developed by Triple. Yeah, there's a lot of study about it. It's called the half plane extension. So the idea is that if we start with a upper half plane, which is the domain where xn bigger than 0, then for xn smaller than 0, the extended function is defined to be the linear combination of this kind of f x prime and then comma negative bj xn. And then we require this kind of aj and bj is satisfy certain algebraic conditions. So by choosing the m sufficiently large, by choosing this kind of aj and bj, enough many aj bjs, we can see that this E1 is bounded in some Sobolev space and CK space, for this case, not too large. And then we can also show that this is what I believe is mostly done by Triple, that this E1 is bounded in Besop space and bounded in triple resolving space for a large range of this PQS. Okay. So yeah, so let me try to recap what is the definition of Besop and triple resolving functions. Yeah, I think Ryan also made a good remark. They talk about certain kinds of things in a very generalized settings. And then in our cases, I only focus on things on Rn. And then when we talk about things on Rn, everything's good. So we can use little Paley decomposition to define that. And then let me recall that what's the little Paley families. It's a families of functions Vj, j from 0 to infinity. It's a Schwartz functions. It satisfies the scaling conditions, the moment conditions, and the approximate identity condition. So once we have this, then we can talk about the decomposition of F into the sum of this kind of Vj convolved F. Then when we raise it to the power of 2 to js, and if we take the LP integral, then the LQ norm, then we got the best of norm. And then if we take the LQ integral, then the LQ sum, and then the LP integral, then we got the triple Rizorki norms. So certainly this norm depends on the choice of phi, but then one can show that different kind of phi will result in a equivalent norms. So yeah, so this is the following result shows. It's different choice. It's still bounded in best of space, and it's still bounded in triple Rizorki space. But and then in our talk, I should also remark that we only for triple Rizorki space, we only care about the case where p is smaller than infinity. Okay, that's because when p equals to infinity, I think the Feynman-Stein's inequality will fail. So yeah, if you are familiar with the definitions of best of space and triple Rizorki space, you probably see that we are using a different kind of characterizations of little Paley families. So in the classical settings, a little Paley families functions, we require the Fourier transform to be completely support. And then later, I'm going to show you that in our settings, this kind of classical definition does not work well when we talk about the extensions. Okay. So yeah, the space of Bechdel space and triple Rizorki space are defined by fixing one versions of such phi. And then for open set omega, our definitions of best of and triple Rizorki space is to be the restrictions of those functions defined on Rn. Okay, so this A here would be always refers to either best of space B or triple Rizorki space F. Okay, I think this one is like the standard notations. So in this settings, if you start with a functions on omega, and certainly you can find extensions on Rn. But then the problem or the extension problem is that we want to find uniform way that map this F to F tilde, which I think if F is not really good, then probably we don't have a good characterization about this one. Yeah, and then also just a few recap about how the best of space match with the how the best of and triple Rizorki space match with the classical space. So the BS infinity is the whole sigma space, and the DFP2K is equals to the classical subleft space for P is not equal to the endpoint. And yeah, there's also FPSS P2S space coincides with the Bessel potential space. Okay. So back to some discussion about the extension operator. Yeah, there are a lot of different construction and a lot of different study about this. And the half-plane extensions, we actually know it's bounded in certain best of and triple Rizorki space. So we are able to construct this extension on infinity domain. And then the study of Lipschitz domain, it's I think yeah, it's the subleft extension starts from Calderon, and later its method is extended by Stein, as what Ryan also mentions in his talk. But I should also point out that Stein's extension works well for L1 functions. But if we want to talk about extension of distribution, then the Stein's operator probably does not act well on that distributions. And yeah, that's how Rychkov goes in, and he shows that we can find an extension operator to extend the distributions on Lipschitz domain. Okay. And yeah, and then for the domain which is rougher than Lipschitz, there's also certain extensions, or we can still talk about extension operators. So Peter Jones has a really good, famous paper to talk about subleft extensions. And also, I think Galia just mentioned that this one also works for certain BMO spaces. Okay, so our focus here is right in the middle. It's Rychkov extension operator. It says that on the bounded Lipschitz domain, we are able to find an extension such that it's bounded in all the best of space and all the triple Rizorki space. Okay, so yeah, in order to talk about our main results, I should go over a little bit about how Rychkov constructs his extension operator. Right. So by taking the partition unity, we only need to care about the special Lipschitz domain, which is the upper half part of a Lipschitz graph. And then in our cases, we sort of want that the gradient of the defining functions is bounded by 1. In that cases, if we points in the omega, and if we try to add this point with another point in this positive cone, then the sum will also lays inside omega. And this is actually a good thing, because if you start with a temporal distribution of omega, and if we have a Schwartz function which supports its negative cone, then we see that the convolutions, it's actually well defined in the neighborhood of omega. This is because, so if you check this condition, so x minus y, it's always lays inside omega, meaning that this convolution is always defined. Yeah, so, and Rychkov's construction require us to use the little bit decompositions. So I just recall it in the top here. And his idea is to find certain families of Vj and psi j, such that if we talk about the convolutions of Vj and psi j, this is the little bit family. And most importantly, Rychkov shows that we are able to construct certain kind of Vj and psi j such that the physical support is strictly lays inside the negative cone. Okay, so if you want to use the classical definitions where those Fourier transform Vj and psi j as CC infinity, then you realize that this physical support conditions, you just have no hope to achieve it. Okay, so that's the reason why we need to use this certain kind of general versions of little petty families. And then we can talk about the extension operator now. So we start with a temporal distribution F. We take a convolution with Vj, and by the support condition of Vj, we know this guy is a smooth function defined in omega. Now it's just defined locally. What about taking a cutoff by the characteristic functions? Now it becomes an L infinity local functions. It's globally defined. And then by taking a convolution with psi j again, and it's just be a C infinity functions. Then the EF is defined to be, we're taking the infinite sum of these double convolutions. And if we restrict our focus on omega, you can see that the EF is merely just this double convolution of Vj and psi j and F. So the cutoff function just disappeared. And then that's why the E is indeed an extension operator. And then by using some kind of estimate on maximum functions, Rychkov shows that this E is bounded in Bezoff space and triple resorting space. Okay, so now we can talk about our main results. So in order to make things a little bit general, we generalize a little bit about little petty families. So in this case, if we don't need approximation identities, we just need moment conditions and scaling conditions. And then we define this operator, I just call it T. There's no any good names. It's just to be double convolutions ratio to the power of JR. And then our results is the following. So this TR is defined on temporal distribution space, and it loses exactly R many derivatives in Bezoff and triple resorting space. So if you take R as some negative numbers, that's actually gain negative R many derivatives. Okay. This one mostly follow from Triple's results. Most follow from Rychkov's results. And the second one and the third one are new. So we show that if you start with certain operators, TR, then you can write down as the derivatives of some kind of operators. I call it T R minus M. So the new operator will actually gain M more derivative than the original one. Okay. And similarly, we can also think about TR as some kind of sum of this another T composed with phi alpha, the derivative of alpha. Okay. And then this one basically means that this kind of families, we have certain kind of anti-derivative properties. And the last one is the smoothing estimate. And the quantitative smoothing estimate, we start with a kind of F P infinity S space. And then the TF function restricted on the complements of the domain will belong to certain weighted subleft space. Okay, so the last result might be a little bit abstract, but I just want to point out that if we apply our results on the extension operators, this one will shows that if we care about just P equals infinity, this one will shows that if we start with a CK functions, then the extended functions will always be C infinity. And then it's this M derivatives of the extended functions is bounded by the distance to the power of K minus M. So you see that the orders of derivative will actually coincide of the orders of the blow up to the distant functions. Okay, so this one is kind of like just the results for Whitney extensions. Okay. And then, yeah, let me just advertise again for how good the Rychkov extension operator is. So even if we consider half-plane domain, if we consider half-plane extensions, we might see the half-plane extension is not a good extension, because if we have a function that has singularity in the domain, then using half-plane extension, the singularity just reflects outside the domain. So we have just tons of copies of this kind of singularity, it just bounce off the domain. Well, if we consider Rychkov's one, it would just be a smooth function. Okay. Yeah, and then that's just a side remark for the this kind of smoothing estimates. And then for the last maybe 5 or 6 minutes, let me just briefly mention about what motivates us to study such kind of refined estimate to Rychkov's operator. So yeah, our study, it actually comes from a study from zero complex variable, where we generalize Xiang Honggong's results on study of the d-bar equation on strictly zero complex domain. And then in his results, he gives a Holder estimate with the assumptions s is bigger than 1. And then we lower the assumption to be s bigger than 0. Yeah, but our concern is mostly about soft left estimate. So the idea is actually to estimate this kind of integral operators, where this K01, you don't really care about what it is, but what you need to notice is that we have commutators of the derivatives and the extension operator. So as I said before, when we talk about Stein's extensions, if the function is not L1, then probably we cannot define the Stein's extension. And then that's actually what the difficulties of Gong's result is that if the s is smaller or equals to 1, then it's very likely the function f is not W11. And the function f is not W11 means that we probably cannot take a commutators on f. So our improvement, or the key improvement for us, is to replace the Stein extension by Rychkov's extension. And now at this moment, the commutator is always defined. And in fact, we can get a really nice result from the smoothing estimate. That's our assumption is that s bigger than 1 over p. The reason why we have to take this assumption is that if we start with the HSV functions, then the commutator will actually lays in L1. So usually, if we just think about arbitrary extension, then the best one that we can hope for is just h s minus 1p. And since s is smaller than 1, it's very likely that we can just have a distribution, not a L1 functions. Okay, so that's how like a simple application to the smoothing estimate. Yeah, but we can do something more. By studying the Rychkov extensions, we are able to prove the equivalent norm results. So if we have a bounded Lipschitz domain, then we shows that for every best of a triple resolving space, where of course a p goes need to smaller than infinity for the triple resolving space, we are able to show that the norm of the original functions is bounded by the norm of its derivatives. Yeah, so this result is known for smooth domain with all the best of space and triple resolving space. It's also known for Lipschitz domain with sublet functions and Holder functions. And then I would have to say that the difficulty to prove this result is that simply knowing there is 6 extensions operator, it's not enough. I mean, yeah, so in most cases, we have to study the structures of the extension operators. So yeah, I should also say that this expression here is also mentioned by Triple, and I think he's proved using a different approach. Yeah, so I think for the last maybe I'll take 2 minutes to talk about the proof of this results. So the difficulty, it's actually only one side. It's to show that the norm of the original functions is bounded by the norm of its partial derivatives. So how does our results apply? Okay, so let's recall that if we have a certain t operators, then we can write down as the sum of certain t operators composed with its partial derivatives. Where the new operators, it gain exactly n many derivatives. Okay, so by writing down the expression of the Rychkov extension, which is the double convolutions, we take off its 0 order terms, and the rest of the order and the rest of the sum, it's our like a T0F. Okay, and then our result says that you are able to write this T0F into the certain T negative M acts on the partial derivative of f. Okay, whether this new operator it gain m many derivatives. Okay, so yeah, so the zero order term is actually a good thing in the sense that if we take the best of Tribole-Wilkins norm, it can just replace by f itself, and it gains arbitrary many derivatives. So here the order can it not has to be s minus m. It could be s minus any large numbers. And then the term we have, it's a t negative m here, and it actually gains m derivatives. So if we talk about the A PQS norm of this guy, it's actually bounded by the A PQS minus m norm of this guy, which is the partial derivatives of f. Okay, so now we have the norm of f is bounded by the norm of its derivative, which is the goal here. And that's basically how we prove this equivalent norm results. Okay. Yeah, and I just want to mention that this result, I think this kind of true property, we can actually talk about things on like general classes of extension operator. So whenever we have extension operator, we can ask whether we can find this kind of commutative properties, and whether we can talk about the talk about the smoothing estimate of the extended functions. Yeah, certainly we can actually talk about whether the Jones extension operator have this kind of property if this omega just a locally uniform domain. And then we can also try to apply this thing about if we just consider Rychkov's extension, can we do this kind of estimates on a weighted best of Tribole-Wilkins space, or maybe some other kind of space like an isotropic best of Tribole-Wilkins space? Yeah, I think that's all I want to talk about. And thanks for your patience and thanks for your attention.